That's the introduction. Now let's look at the first section, which is production accounting and conservation equations. So, what is thermodynamics about? Basically, it's a study of the behavior of matter based on four conceptual quantities, which are mass, momentum, energy, and entropy. And there are rules guiding the changes of these quantities, known as the basic principles. And we're going to express these principles using production accounting. So let me start with drawing a system diagram. Suppose we have a system like this, and suppose the dashed line is the system boundary, and sometimes we call it control surface. And there are four properties described in the system, which are mass, momentum, energy, and entropy. And we can have inflow of work, heat, mass, or momentum into the system, and we can also have outflow, and there can also be forces applied to the system. So production accounting basically tells us that the production of a quantity equals outflow minus inflow plus the accumulation inside the system. And in the next, we'll apply this production accounting to the for different. I want to mention one thing very quickly. So depending on how we draw the system boundary, we can have the difference between the control volume and the control mass. For control volume, the system boundary moves independently of the mass. So we can have a non-zero mass flux across the boundary, and in the contrary, controlled mass is a system boundary that moves together with the mass. So there's no mass flux across the boundary, and this is a summary of controlled volume and controlled mass. So let's apply the production accounting to the basic quantities to get a mathematical equation for the basic principles. So depending on whether we choose controlled volume or controlled mass, we can have different representations of the system, but both can be correct. So let's start with conservation of mass. Suppose let's start first with control mass. Suppose this is a system, and since there's no mass flux across the system boundary for a controlled mass, production accounting basically tells us that production equals to accumulation equals to delta M, the change of mass in the system, equals to 0. So that's very simple. Now let's look at the case for control volume. Since there can be flux, since there can be inflow or outflow into the system, we have to take that into account. So the first one is the net flux, which is an integral of control surface, rho v dA, and also there's a accumulation term, which is partial t control over the control volume density dV, and that equals 0. For a system with specified inflow or outflow, we can have a simple form, which is m out, the mass, the outflow mass flux, minus m in dot, plus dm dt, where m is the mass of within the control volume, equals 0. So these are the two forms of the equation of conservation of mass. So next time we'll talk about conservation of momentum. For momentum, Newton's law tells us that the production rate equals to the summation of forces applied to the system. So for controlled mass, production equals to accumulation equals dp dt equals to sigma f. So for controlled mass, controlled volume, we have inflow or outflow. So sigma f equals to production equals to outflow, which is m out dot v out minus dot v in and also plus the accumulation term. So first law of thermodynamics tells us that energy is conserved. So when we apply product accounting for control of mass, we still have inflow or outflow, and these are through work or heat interactions. So the equation looks like 0 equals to production equals to the outflow rate into the system minus the inflow rate of the system plus the change of energy inside the system. For control volume, we have a additional term associated with mass transfer. So the equation looks like now the W and Q are net work and heat flux. So it's just the difference between W out and W in. And we have a additional term associated with the mass transfer. And also the accumulation term. Now let's take a closer look. The mass-specific energy, E, can be further expressed as internal energy plus kinetic energy and potential energy part. And the heat transfer Q can be expressed as heat flux. Integration of heat flux across the control surface. And work transfer can be expressed as shaft work, which is a part of work that can be extracted from the system to drive a shaft or do some other mechanical work, minus the surface work, which is the surface force times the surface velocity. And this term equals to the stress term plus the pressure term times the velocity of surface times and this is the shear stress and this is normal stress equals to pressure. And normally shear stress is much less than the normal stress, so we can just neglect this term. So putting all this together, we can get and notice that this is just the total entropy. For entropy, we have second law of thermodynamics, which says that the production rate of entropy is always larger or equal to 0, which means that entropy cannot be destroyed. Yeah, it can only be created. So for a control mass, this basically says that production rate we often define as sigma dot. Production rate equals to the outflow. For this case, this is Q out dot minus T out minus the inflow. This will be Q in dot divided by Q T in, and plus the rate of accumulation is in the system. And for control mass, and now for control volume, we have additional terms associated with this mass transfer. And dt, and entropy generation is always larger than 0. This does not necessarily mean that ds dt is larger than 0, because we can have transfer out of the system, but it does mean that the production is always larger or equal to 0. So this is the end of the first session. In the next session, we'll talk about more about entropy and also exergy and efficiency. So I hope you enjoy this video, and please feel free to leave comments or feedbacks. I guess I'll see you in the